Good. So uh, let's move on to allocation profiling. I like the idea I heard from one JVM engineer that if you want your Java programs to be as fast as in C, write them the way you would write them in C. So forget about automatic memory management and these kinds. Indeed, allocation and garbage collection caused by this allocation is a common problem for in many cases, and that's why there are so many conference talks about avoiding allocations by going to native or unsafe, using of heap structures and involving garbage-free algorithms and so on. But at the same time, or we being Java programmers, we don't want to use these tricks and hacks all the time. So we want to use normal Java with streams, abstractions, and so on. Well, you would say that when I develop a program, I know how much it allocates. But in practice, it's not sometimes obvious at all. For example, consider this simple program that counts the number of iterations during 10 seconds. How many objects are allocated there and which types of the objects. Fortunately, again, many profilers have built-in allocation profiling mechanisms. In VisualVM, there are even two of them, memory sampler and memory profiler. Our memory sampler is a mechanism when a profiler just takes a histogram of all classes in Java heap at the moment. So it basically takes snapshots of the heap with no objects, just only a histogram. And in the above example with local date time, could you imagine that this example could even allocate a concurrent hash map, many concurrent hash maps? Nonsense. But I indeed hit such a bug in real application. It was caused by wrong time zone on a server. The time zone that Java doesn't know about, and that's why on each call of local date time, it tried to recreate zone rules. And if you go to the source code of zone rules, you'll find that concurrent hash map is created there. The problem was fixed, by the way, by just setting the right time zone, which is cached. But anyway, so another approach how a memory profiler works is bytecode instrumentation. What it does is basically adds the instrumentation code to all places where new objects are located. So like with instrumentation profilers, it modifies your code to do additional things. Of course, this approach has a significant overhead. And in order to reduce it, usually such profilers usually optimize it by taking the object sample only each n times. One more way to profile allocations in hotspot is using a special gtrace probe. I'm not sure that it's still actual for modern JDKs, probably not, but at least in JDK 8 it was possible to do that. There are a couple of blog posts. You may check how to do that. But the downside of this approach is that all allocations are done in slow pass-through calling into the VM runtime. Again, big overhead. Other interesting tools is Aprof by DevExperts. This is also an instrumenting profiler, but really optimized one. And another one is Allocation Instrumenter. It's not really a profiler, but rather a framework for building your own instrumenters, rather allocation. So you can, with Allocation Instrumenter, you can program it, to intercept specific kinds of allocations and invoke whatever callbacks you want on whenever allocation happens. So I took this simple artificial example with datetime and measured the overhead of the above approaches, and don't look into numbers. I just wanted to show that all of them have huge overhead. Sometimes it slows down the application by the order of magnitude. But we have flight recorder and mission control, which when I took it also has the ability to profile allocations. When I took this and run profiling, I found that it has really small overhead. So so small that we can even use it in production. It was a commercial feature for a long time, but now it's open source and available for free since JDK 11, and Flight Recorder was also ported recently to JDK 8. And Flight Recorder not only says what objects are allocated, but gives you the exact stack trace to the places where these objects are allocated from. But interesting thing, it doesn't show you the size of the allocated object, but instead some another strange metrics like total TLAB size. To understand what it means, let's see how allocation works in hotspot JVM. So in the fast path, the allocation is done inside the thread local allocation buffer. So each thread has current one active allocation thread local allocation buffer, and it can allocate new memory right away from this buffer by a simple pointer increment with no synchronization at all, because the TLAB is reserved for this particular thread and no one else can touch it. If there is not enough TLAB space to allocate new object, there are two options. Depending on the remaining space in TLAB and the size of allocated objects, a new object can be allocated directly in Eden or young generation, or the existing TLAB can be discarded and a new one is allocated. So what we have is the fast path allocation is done inside TLAB by simple pointer bump technique. And when TLAB allocation is not possible, there are two fallbacks. The allocation in a new TLAB, allocation of a new TLAB, and allocation outside TLAB. The idea of allocation profiling for a low overhead allocation profiling is to profile only slow path allocations. And that's what Flight Recorder does. And that's what Async-profiler does as well. Actually, Async-profiler just intercepts exactly the same allocation places in the JVM code that otherwise notify Flight Recorder. So the idea of allocation sampling in Async-profiler is simple. Just intercept these places in JVM runtime code that do slow path allocations. The good news is that it works even in JDK 7, in OpenJDK, and doesn't rely on commercial features. So even if you're still on old JDK, you can use allocation sampler in Async-profiler, and it will be fast and low overhead and provide exactly the same amount of information as Flight Recorder does regarding allocation profiling. Since JDK 11, a new API appeared in JVM tool interface, specifically for profiling allocations. The idea of this API is also based on TLabs, but now the allocation samples not only when TLab overs, but an additional boundary is added to TLab, and this boundary can be adjusted depending on how often do you want to sample allocations. For example, if you want to sample every 100 kilobytes allocated memory, then in a new TLab, this virtual boundary will be set to 100 kilobytes. Okay, let's see how it works. Let me show you the code. First, this code reads a large file containing a key value pairs. They are just separated by spaces and a colon, and the code parses the key and parses value as a number and puts everything in a hash map. So pretty simple and straightforward case. When I profile it with, let's run it, we profile it with just CPU profiler as usual. Oh, you see the reading 7 million elements took 15 seconds. And if you look to the CPU flame graph, you'll find that the most time is spent in garbage collection. So obviously, there is not much to optimize from the CPU side here because we need to reduce the garbage collection pressure somehow. So here's where the allocation profiler will help. So to use it, just we add a lock option as an event. And let it run once again. 5 seconds will be enough. Yeah, we got another flame graph, but now this flame graph shows allocated objects, and the stack traces represent where these objects are allocated from. So what we see here, that more than half of all allocated objects are allocated in string split in this part. It's quite understood because each split creates a new array which we are not actually need. So the first optimization would be to replace split with manual splitting. So we just find a column and cut everything on the left and the right side. Okay, let's run our modified version and measure what happens. I'll also collect profile. Okay, we saved a couple of seconds by this simple trick. And let's see our updated profile. Okay, there is no more split here. The next big part is substring and trim. And actually, substring is called, you see, twice from trim and from read map. And exactly what is in the code. First, we construct a new string, and then we construct yet another string by trimming it. We could probably combine these two operations into one by writing our own trim, which will do just one substring. Okay, our next optimization is measurement. Oh, 2 more saved seconds. Good. Okay, what is left? A read line, this one substring, and not obvious what to optimize further. But these flame graphs show us the allocation samplers. But like with the log profiling, we can also profile the allocation size instead of the number of samples. So let's find the largest allocated object. Like in previous example, I just add flame graph total option and run it once again. Yeah, maybe let me run it a bit longer because the test takes more than 10 seconds. What to optimize next? Yeah, what catches the eye in this flame graph is this brown part. What about colors? So this aqua color means allocation in an UTLab. And brown means allocation outside the lab. So you remember there are two possible paths of slow path allocation. Usually the allocation outside the lab means that the object is too large for a new TLab. The size of TLab varies usually between, let's say, 100 kilobytes and a couple of megabytes. So larger objects will definitely go outside TLab. And here, what is located outside the lab is a hash map node array inside the hash map resize. What does it mean? That our map is resized while we fill it, And we know that there are about 7 million elements. So let's just pre-allocate the hash map of the necessary size and see if it helps. Yeah, we fall below 10 seconds. So we are almost twice as fast as our original solution. Good. This way, Async-profiler help us to find allocation bottlenecks and improve our code. Maybe questions on allocation profiling?
Yeah, we have a couple of questions. Yeah, one is probably a simple one. Typically, how big is the TLAB?
Yeah, already answered. From 10 kilobytes to several megabytes.
Okay, right. So 10 kilobytes to 10 bytes. Okay, and yeah, go on.
Yeah, does the volatile keyword change the allocation approach?
Sorry.
So does the keyword change your allocation approach?
Keyword.
Timur, you might have to type in some clarification there. His actual question is, does volatile keyword changes allocation approach?
I see.
Yeah, volatile. Yeah. Sorry, there we go. There you go. Volatile.
Volatile doesn't affect the process of allocation. It just affects how the references are assigned. But no, allocation is still the same.
You have one more question. This goes back to your color legend. Remember you identified the colors on the allocations graph, I believe the flame graph. We're going to have to get you, Andrei, to put a legend up for that. Could you repeat the colors on the allocation graphs, what they represent? Yeah. Thank you.
So
I'm going to type these in here.
Blue one is allocation in a fresh lab, and brown one is allocation outside the lab. So brown ones are usually allocations of large objects.
Okay.
So
Andrew Chen is.
Yeah, I'm sorry. Double check. So the common approach is to pay attention on that on that objects that not fit in a TLAB, right?
Yeah, actually, with G1 GC, the large objects can cause so-called homogeneous allocations. So those allocations that occupy one or more G1 regions entirely in heap, and those usually affect performance badly. So I saw several times how people try to optimize homogeneous allocations specifically. And actually, it's possible to profile homogeneous allocations with Async-profiler right away. I can show you that probably right. Oh, why not showing this right now? I think let me run my first example with use G1 GC, and the event will be I don't remember it by heart. Let me just copy paste it.
He doesn't want us to think he's perfect, Yvonne.
Okay, so actually, this is not the special event or special mode of Async-profiler, but Async-profiler can profile any native function. So this is just the name of the function inside the hotspot JVM, which is called whenever there is a homogeneous allocation happens.
So you basically know that inside G1 there is a such method, and
yeah, I looked at the source code and found this function name.
So okay, easy one.
For those who are familiar with JVM code. But, actually, I haven't tried this, so this will be an interesting experiment for me as well. Let's see. Wow. Yeah, indeed. It showed a couple of homogeneous allocations, and they exactly happened in hash map resize. So where our big hash map is reallocated. So it's quite plausible.
Cool.
More questions?
Yeah, Yvonne, do you want to ask the one from Andrew Chen is actually a hackathon first prize winner. Do you want to?
Oh yeah. Is there a way to set the size of TLAB with JVM parameters?
Yes, there is TLAB size option. Let me write it here. So let's say 10 kilobytes. It's a pretty small TLAB. And let's see if it changes anything. I expect now much more allocations outside TLAB. Actually, yeah, the picture is similar to what we had before, but yeah, looks like 10 kilobytes is still enough for most of small strings and arrays that this test allocates. By the way, there is a special hack that if you want to measure every single allocation in your application, I think you quite seldom want to do these kind of things, or unless you are doing implementing algorithm which is expected to be garbage free. And so it's possible to turn off TLAB at all. I specify minus use TLAB. By the way, this trick works only with G1 GC. With other garbage collectors, the objects can be still allocated in assembly code without going through VM runtime, even if they are allocated outside TLAB. But G1 always goes through VM runtime. So we may see how many objects allocated at JVM startup just to run a Hello World application. Yeah. So it was actually on my plan. We just switched the order a bit.
Okay, but
simple Hello World application, and we need to run profiler as an agent. in order to attach it immediately and profile everything. Start event of no event is a log file. HTML looks like this enough. Yeah, it's all allocations for hello world, and most of them for class loading, obviously. Class loading, yeah. For initialization of method handlers, machinery, and so on. And there are a few interesting ones. Like you see these brown rectangles with no Java stack trace underneath them. So these are kind of strings, characters, and what are they and where are they allocated from? So actually, you probably noticed that unlike CPU flame graph, the allocation flame graph doesn't include native stack traces. It's done on purpose because most objects are located in Java code and there is no need to spoil flame graphs with a lot of unnecessary information. But in these such cases where you do want to native stack traces, you may add them with another option, cstack. Cstack has three options. No, do not record stack traces. FP, use walk native stack traces using a frame pointer linked list. I talked about it before. And another one is LBR, last branch record. It's an interesting option which appeared not so long ago. I'll talk about it a bit later. Let me just start with a simple native stack walking for this Hello World application. Yeah, now we see the same stack traces, but with yellow part from VM runtime. And those stack traces that had no Java frames are actually created from the virtual machine.
Happy birthday. Happy
Catherine, sorry, you're not on mute.
Sorry about
those objects are located from during VM startup, and we see that profiler even profiles itself. Then when profiler starts, it allocates a couple of objects, and these are actually exceptions. And I know why it happens, because it first looks for classes from GDK, from newer GDKs, from GDK 15, and if it doesn't find them, it falls back to older classes. So this class not found exception actually allocates. Since I already mentioned this topic, let's talk about what is LBR.
Yeah, I'm sorry. A small question. You put minus u still up, but how could you repeat that? How would it help us to understand? I mean, without that minus u still up, it will not show us every single allocation, right?
Yeah, the allocations will be sampled only when only slow path.
Okay.
Yes, and this option basically makes all allocations go through a slow path through VM runtime, and this way we catch every single allocation.
Okay, got it. Thank you.
Okay, so let me show you the problem first. I don't know whether I have it on a slide. Oh, looks like it don't have it on the slide, but I know where I do have it. Async-profiler issues page. Yeah. So the problem is then that sometimes when you want to get native stack traces, you cannot do that because the native library is compiled without maintaining frame pointer calling convention. So basically, GCC has a similar optimization that Java does. It skips maintaining the linked list of frames and doesn't preserve frame pointers. And in this case, we get these truncated native stacks. But the modern hardware, as far as I remember from Intel Nehalem processors, they support hardware stack working by using last branch record mechanism. So basically, the processor records all branches, so all jumps in the code. So whether it is a method, whether it is a function call, or just conditional branch, and it also has a possibility to match corresponding call and return instructions and use them to build a hardware-assisted stack trace. And in modern Linux kernels, starting from Linux 4.2, if I remember correctly, there is option to make perf event API to use this last branch record facility for obtaining hardware stacks. And in this case, so even in these cases, you see this was a OpenSSL library. If I profile the same with last branch record mechanism, so I see more or less good stack traces. I see specific functions from OpenSSL. Okay, so shall we move next? Yeah, a few words about Java API of Async-profiler. So, so far we invoked it either as a Java agent, or not Java, sorry, like JVM-TI agent, or from using the command line scripts. It's also possible to profile the application right from within the application using the Java API. How to do it? So imagine that we have some application that takes a list of files and converts it. The conversion process takes 3 steps. It reads the input, converts it to another format, and saves the results, whatever it means. So consider that I want to merge, to benchmark to profile the particular process, and I can explicitly invoke a Async-profiler using the Java API from the code and call start to start CPU profiling, this event name to profile, and this interval in nanoseconds for CPU profiling, in bytes for allocation profiling. And after that, I can call some other method to dump the results. So let me run it to see what happens. Yeah, processes a few files. And prints the profile right here on the screen. That's what I did. So I received the results just as a simple string. I also can use execute method to invoke arbitrary profiler command in the same syntax like with agent. So in this case, I'll dump a flame graph into HTML file. Let me recompile and run it once again. Yeah, here is our profile for converter. Now, for example, we do not want to profile the save results part and read input part. So we're interested only in optimizing conversion part, for example. So we want to reduce the furthermore, we see on these flame graphs that a significant amount of time is spent on garbage collection, and we want to understand whether it is a garbage collection caused by reading input, saving results, or by processing our file. In order to achieve this, we will replace start method with resume method, which actually resumes profiling, retaining all the previously collected results. So in this way, convert file method is called in the loop, but we profile only one piece of it for all files. And then after the process ends, dump a single combined profile for all files. Yeah, now there is only conversion part left, and we see how much garbage collection is caused by this conversion part. Something more about Java API. By default, get instance finds the native profiler library in the Java library path, and it's possible to provide the exact path to library if you wish.
Do you mean where is it on the disk? So just path to
the path to shared library. Okay. Lib async-profiler.so.
Yeah, but obviously you have to have some dependency in your code, right? What is it?
Just async-profiler jar. It was in the package I showed you before.
I see. Is there any Maven dependency?
Not yet, but I hope to add it soon. Actually, there is. I saw a pull request recently.
Okay, so we'll look it forward.
Mm-hmm.
Yeah, I don't see a lot of question about Java API, but if you please. We'll come back to a few questions about allocations. So yeah, that's a very good question from Alexei. What types are on the top allocation frame graph? So in general, the most basic types which can be allocated. For example, sometimes there is a string, but sometimes there is a byte array. And as far as Alex understood, string contains these bytes internally, but it doesn't appear in the flame graph. So what would be on the top?
It does appear. It does appear. Well, I will not redundant, but believe me, you will see there both string objects and byte array or a character array in earlier Java.
Okay. Okay. So, but,
they will be both.
All right, got it. Yeah, and another question from our invited specialist from Real Logic. Thank you very much for joining. Maybe that's a bit more general, but can Async-profiler show off CPU thread blocked or waiting in native code? For example, thread that waits a slow SQL query and it's blocked during socket read, waiting for the database to deliver the results.
Yeah, the profiling in wall clock mode will show you such such threads, such calls too, and that's the big difference from GFR and from perfmap agent. They do not do this kind of profiling, so it's I can say unique feature of Async-profiler.
Okay, yeah, that's great. So probably you will show us on the extended Q&A session, if you please.
Yeah, actually, I did show it before when I measured the startup of the Spring application. So they were in a wall clock profiler graph. They were. Okay, maybe I have it. Let me.
Oh, okay. We'll cover it later. Okay, so probably we'll have to rewatch. So there will be an record for that.
Here it is. Yeah, here's the wall clock profiles. He'll have a wait. So where thread is waiting on a lock, and you can see the total time spent in waiting for this thread.
Okay, cool. Yeah, thank you. It's done. And yeah, another question about allocations. Also, how can we fix optimize brown colors? That means that where we optimize, where we allocate outside of TLab. Could you talk about some optimization approach in such case? But I think that depends from application itself, correct?
Yeah, of course, it depends on the application. I can just tell a few random examples what we did in our projects. The big allocations are also bad for. We used to use CMS GC when we ran our applications on Java 8. And CMS doesn't work well with when large objects are promoted to old gen, and because this causes fragmentation of the old gen, and can finally lead to a situation when there is space in the old gen, but due to fragmentation, you see promotion fails. And what we did is For example, a large bit set, which was a large long array, split it into an array of smaller bitmaps. Another example is to replace a heap byte buffer with a off-heap or direct byte buffer. These kind of optimizations.
Okay, got it. Thank you. So basically, some general approach to modify your code to use less such kind of applications, or just reducing them at all and move maybe to off heap.
Yeah.
Right. Okay, got it. So does Async-profiler integrate with the IntelliJ IDEA? Oh, that's a nice one.
Yeah, and this was actually on my plan. Let me go directly to this.
Oh, cool. Yeah, let's move on with this.
Mm-hmm. You'll probably ask why run all these examples in console, not from IDEA, because I'm a Windows guy, and there is no Async-profiler on Windows yet. And but here I launch IDEA from a Linux virtual machine. Okay, here's my Linux IDEA. It's early access preview, which I downloaded just a few days ago. So what do we have there? I need to mention that Async-profiler is available only in Ultimate Edition. So you need to pay for it, but I would say this feature worth paying. Right here in the Run toolbar, there is a new button, Run with Profiler, and here are 3 new options. Run with CPU profiler, with allocation profiler, and Java flight recorder. Actually, the first 2, CPU profiler and allocation profiler, are run the program with async profiler attached in CPU and allocation mode, obviously. Okay, let's do it and see what happens.
Yeah, just double checking. Is it out of the box, or you
yeah,
have
out
to
of the box?
Out of the box. Go.
So so saying that we are profiling, we can stop it anytime you like. And see the flame graph right in the IDEA window. This is not the same HTML flame graph, but the idea is the same. So it is also colored Java frames with this brown and blue is native part, and even kernel stack traces are also there. You also can zoom in, zoom out. And just start typing to find something. Like, yeah, and the matching part will be highlighted immediately as I type. So, and what I like most about it is that you can immediately split profile by threads, or merge all threads into a single graph.
Yeah, that's a nice one.
Well, the same for allocation profiling. Let me show. By the way, it's possible to configure profiler options. Yeah. So in the configuration window, you can set options, custom options for CPU profiler, for allocation profiler. The syntax is the same as you saw when running the Async-profiler as an agent. And so you see here's a version of the agent. It currently uses a bundlet. It's possible to specify the external path to the profile library. So let me run the same with allocation profiler now. Yeah, you see that it automatically adds agent path with async profiler to the command line. Yeah, here it is. Again, like with HTML flame graphs, the allocated objects are highlighted. You also can search, filter, and so on. Split by threads. Very nice. And besides the flame graph, you can also see the results as a tree or as a flat profile with the hottest methods sorted by the total number of samples or the self time. In case of allocation profile, this is not the self time, but the number of allocated objects. It's also possible to attach profiler to an application that is already running. Here is from a menu, attach profiler to process. I can even attach a profiler to myself because IDEA, you know, is a Java application, and I can profile IDEA with async profiler bundled into the same IDEA. Let me do some actions to make the profile meaningful. Okay. Yeah, here's a flame graph of our idea profiling. A lot of compilation, of course. Oh, really deep stacks. Also, you can open the profile collected by an external tool. For example, you collected the profile before in a collapsed stack format or in Java Flight Recorder format, and IDEA can open both. And it does it really, really quickly. In this case, I opened a file which is 100 megabytes in size, and you see it showed it almost immediately, and it's very responsive. So it's a pleasure to work with such large frame graphs in IDEA. Okay. Probably that's it about integration with IDEA. Any questions?
There's a question about whether you have support for Eclipse planned before Ivan takes Sridhar's next question. So are you planning support for Eclipse?
I don't. If somebody will, it will be nice. I'm ready to review pull requests. Actually, I think this integration more from Eclipse side rather than from async profilers.
And there's one more around IDEA. Will it be working on Windows eventually, do you think?
I think so. I know that JetBrains is working on a Windows port, and they're even going to present some kind of prototype in 2 weeks on Joker conference. So there is a conference session announced about this, and I'm also invited there as an expert. So I'm looking forward to watch it myself.
Did you collaborate with them somehow? Did they need some I don't know hacks in the profiler itself?
Yeah, we keep contacts and exchange ideas, feature requests. And interestingly, this is done both sides. So they request features from me, and I try this integration in idea and provide my feedback to them.
Oh, cool. So, I mean, but that's only about Windows or about the integration with the IDE itself?
About general integration.
General integration, got it.
Okay.
Yeah. So, and the last question, and then we move on. In the Java API, is there an option to dump the results when the process ends? I mean, yeah.
Yeah, it's actually a good question because, well, it's not done by default, but you can install a shutdown hook to invoke a dump command.
So you have to do it to yourself.
Mm-hmm.
Okay, got it. Thank you. So we can move on.
So I believe we have too many topics to cover, but so a little time for so many topics. Let me choose the most interesting, probably. Well, what I wanted to show also is like how Async-profiler helps to find non-trivial native memory leaks. Consider a simple servlet that not servlet, just a small web application that gives you an image by ID. And it gets an image from the resource and sends it as a byte array. So I run an example that calls this get image in a loop. And what I see here that the usage, the resident set size of the Java process constantly grows. So it keeps growing and growing and growing. And there is no Java level leak. So this native memory that is leaking, and Async-profiler can help to find the source of this leak. For this, it can we can use malloc event, but this is not the separate event. This is a trick that I already showed before. It just hooks to an existing native function and profiles calls to this function. So here I profile all calls to standard system malloc. Yeah. But profiling malloc is not always useful for finding native memory leaks, because if something calls malloc, it doesn't necessarily mean that this is a leak, because it can shortly freeze this memory and there will be no leak. For example, we see here Unix file system, Boolean attributes, whatever. So there are a lot of malloc called from the compiler. But if you dig deeper about how malloc works under the hood, you'll know that, well, actually, this depends on the implementation of malloc. On some systems, generally, malloc asks memory from the operating system by calling mmap system call with big chunks. So it preallocates big chunks with mmap, and then it increases the amount of used memory within this chunk by by committing more native memory by calling mprotect. So what you can do is to profile mprotect call instead of malloc. Now you'll see the places where the allocator increases. So these places are exactly related to the growth of the resident set size. And what's nice about that is that we can track them down to our Java code. So they are actually called result. This leak is called by inflator, which tracks down to our get image and get resources stream. So the problem here is that we get the input stream, but do not close it after the method ends. So the native memory obtained for the inflator. And why is inflator here? Because the resource is in jar file, and in order to unpack it, the JDK needs to create inflator. Of course, this inflator has a finalize method, which will be sometime called. So strictly speaking, this is not really a leak. This will eventually get cleared once garbage collection happens. But the problem is that a native memory can't end up earlier than, if we have a large heap, then native memory can end earlier than we exhaust the Java heap.
Yeah, I'm sorry. A small question about mprotects. Why is it so? As far as understood, we allocate something, and once we use a new memory, right? That we previously did. We have to.
Yeah, this depends on the allocator algorithm. Some allocators just use mmap and that's it. Other ones, like standard allocator in libc and in GNU libc, it well, requests the memory by big chunks by calling mmap, but it just resources the memory, not yet commits it, and commits this memory by smaller chunks by calling mprotect on the part of this bigger chunk. I explained this some time ago in my presentation about native memory. It's called footprint of a Java process. So you may easily Google it. There are presentations available on YouTube.
Yeah, I'll leave a link on the presentation later. But why is it cause of memory leak, or maybe some mark and to pay attention?
What exactly?
mProtect. So we start to measure mProtect to say that probably the place where the memory leak will solve.
This is because when there is no enough already allocated memory for a malloc allocation to work. So it increases its own native heap by calling mProtect. So by profiling mProtect, we basically find the places where the malloc increases its native heap.
Ah, I see. Okay, got it. Thank you.
Well, similar interesting example. Well, just dummy test that reads some file in a loop, and that's it. Just reads and even do nothing with it. So when I run it, I don't see a memory leak in a common understanding. But here's another kind of leak. You see that the free memory in the operating system is constantly decreasing while the application is running. But at the same time, the resident set size of the Java process doesn't grow. So it's a kind of interesting leak. The total memory in the operating system is decreasing, but this definitely is related to our process, because if I stop the Java process now, then the memory will stop decreasing. And what does grow is a page cache. So this is memory, so it's just system cache of the files that accessed on the disk. And it's not obvious how our Java application can affect system caches. And to discover this, again, Async-profiler can help by profiling operating system trace points. So if we run perf list, which will show number of events available in perf, and in particular, the trace points events. So Async-profiler, like perf, also supports trace points. So what are trace points? These are predefined places in the Linux kernel that can be intercepted, hooked, profiled. So we'll look here something related to page cache. Yeah, here is the one. So this is a trace point, which is called that when the operating system needs to add a new page to the cache. And what we can do with Async-profiler is to profile this trace point. I'll just put this name of the trace point instead of the event. And as a consequence, you will indeed get a flame graph that leads from the page cache, from the brown kernel part, down to our Java code. So what in our case, causes a page cache flooding is a log4j logger. And we hit a similar problem once in production. So this example came from a real scenario. Actually, the log rotation was not configured properly. And as long as the application was writing more and more into a log and the log wasn't rotated, and while the file is open, so the page cache grows. And we could immediately fix it by configuring the log rotation. Okay.
Yeah, but a small question from me. I mean, you obviously an expert and you know how it works internally, but for you know, not so smart people like me, for example, how to find that event that you just showed us? I mean, how to understand which event you have to pay attention to?
Yeah, this actually requires certain experience. I didn't know about these trace points before, even myself, but I saw that the page cache is growing, and page cache, it doesn't even belong to a particular process in the system. So it's a property of the operating system. So in order to find the reason, we need to trace something inside the operating system. And what can be traced in the operating system are these trace points. So their names speak for themselves. So the points in the kernel that can be traced. So I opened perf list and tried to look through this list, finding something that resembles something that has a relation in its name to page cache.
Okay. Yeah, that's a non-trivial task. I mean, I try to, from my experience, I try to do it myself. But when I open this list, it's huge, and say, okay, I know nothing about it. And close it.
Another very interesting part in this list, so that can be traced, are syscalls. So you basically can intercept any syscall from two sides when on syscall enter and on the exit from a syscall. So basically anything like if you want to find where files are opened, where user permissions are changed, or directories are created, or whatever. So you can hook into this trace points, syscalls for the particular syscall.
Yeah, thank you. And if we have to choose and pick up the examples, so could you demonstrate, as you promised, how to monitor and profile application which react only at some events, like reactive programming and stuff?
Okay, so my idea was that it's well, you can profile the whole application, but you see the problem of flame graphs, that it is combined, aggregated data.
Mm-hmm.
So in order to find the events we are interested in, it would be nice to record the events individually. And Async-profiler can do this. It supports writing all samples, recording every single sample it gathers in a GFR file in a format compatible with flight recorder, which can be opened in Java Mission Control. And okay, let me show you an example. Yeah, I think this. Well, in this example, you don't need to read the code. Just I'll show you the result. So what happens in this case that we are worried about some CPU spikes that happen every 5 seconds. So if you use regular CPU profiling, then probably those spikes will be hidden among other garbage. But we want to detect exactly these spikes. So what we can do is to profile, make a GFR recording. Yeah, here how to do it. So the command line is the same. The only thing I changed is the file extensions. So the profile detects that if it's GFR extension, that it switched to flight recorder format. And now we can open this recording in mission control. It takes some time. And yeah, what we see is these spikes of CPU load. Starting from Async-profiler 2.0, it also records the CPU load of the machine and the JVM process. So we can find those spikes and match them with samplers. And clicking on them in mission control, we find the stack traces, these problematic stack traces, and find what are these events. Another interesting presentation of this timeline is a flame scope. So do you familiar with flame scope? It's a tool also by Brent and Greg. So the idea is to present events in like a heat map, where the more intensive is color, then the more events are there. And then you can change, you could select an arbitrary range of this timeline and build a flame graph for this particular timeline. Well, I'm afraid I don't have a flame scope installed here, but Async-profiler has converter. Do you remember that package has a converter jar? And one of the tools there is GFR to NFLX. This is exactly the tool that converts GFR recordings to Netflix format. So the format supported by Flamescope tool. Okay, does it make sense?
Yeah, I think it does. But okay, let's show how it looks like a bit later. Okay, maybe, or it's okay.
So as to me, I'm I can sit here till late night, but I don't know if you guys are tired of my endless talk.
No, I ask in the chat, are the guys are okay to stay a bit longer? And so I see some of readiness for that. Yeah, they say we are good, and so you could finish.
Should we ask again if people could just put a plus sign in if they can stay till like maybe what 2:30 or? Okay, yeah. We're getting pluses. We have a couple people there, and there's a few questions too in the Q&A. So
yeah, let's finish with the talk and then we'll go to the
keep
Q&A.
going. It looks like people are willing
since I
to
already
stay.
opened Q&A,
Yes.
I can answer those two questions. So what will happen if you profile a trace point that doesn't lead to a Java app code? Well, it will appear in the flame graph, but just as a in a red color, just as a native part with no green frames underneath it. So it's perfectly okay. So is there a tool which allows to build flame graph which gathered from dozens of instances? Yeah, good question. Yes, it's possible. So actually, there are two ways to do this. First, to collect profiles from multiple instances in either collapsed stack traces format or in GFR format. So both formats are fine, and they can be combined together just with a simple file concatenation. And you'll get this big file, which will contain the, and then this combined file can be opened, for example, in IDEA or using converter. Async-profiler also has a converter to convert collapsed stack traces format to a flame graph. So it's called flame graph tool. It gets collapsed and outputs an HTML. That's it. So no more questions.
Yeah, I think we can keep going.
Okay. Let me see what else interesting I can. Yeah, this is a simple but still interesting example how we can profile hardware performance counters, not just CPU instructions, but some more interesting counters like cache misses. This example starts two threads, and these threads are doing exactly the same thing. They just increment some random element of the array many times. But the only difference between those threads that they even allocate the array of the same size, so 1 million elements. But the first thread touches only a small part of this array, and the second one touches the whole array. So if you use usual CPU profiling, first let me show that one thread is already finished in 5 seconds. The second thread is still working. But it does exactly the same amount of operations. So both threads do 1 billion array operations, but one thread takes 5 seconds, another 35. So let's see with the regular CPU profiler what's on. Well, nothing interesting. It tells us that both threads took roughly the same amount, just 50% and 50. And the stack traces are similar. So measuring CPU cycles is useless in this case, but still the problem exists. And it can be found with by profiling cache misses. So now we try to catch places in the codes that lead to processor cache misses. And now we see that the flame graph is clearly dominated by the large or the thread that accesses the whole array. There are a lot more cache misses, and that's why it works slower.
Yeah, that's pretty cool. Is it possible to find a false sharing then? I think that's something very similar, isn't it?
Yeah, I think that yeah, maybe not for false sharing. It's even better to profile last level cache misses. I had I had a few slides about what we can profile with Async-profiler. So I talked about these things. These are built-in profilers. So about kernel events, predefined kernel events and trace points, and events from performance monitoring unit, cycles, bus cycles, cache reference, cache misses, and both first level cache misses and last level cache misses, and TLB misses as well. Mispredicted branches. By the way, here's a home task for you to write a similar example that will show a similar profile for two threads if we profile CPU, but completely different profile if we profile branch misses. And okay, what else can be profiled? So functions breakpoints, I already showed an example with profiling malloc and mprotect. And a specific case of profiling functions is to profile virtual functions inside the virtual machine shared library. And among interesting things, there are operations that are executed on a VM thread. So they are basically the stop the world operations. So if you want to find the reasons of the stop the world pauses, we can profile VM thread execute, de-optimizations, humongous allocations. We already seen that today. An interesting example with throwables. Let me show it. Yeah. So this is some code that scans for existing classes on the class path and perform some calculation on them. Doesn't matter. So let me just run it. Class analyzer. Well, and at some point, this example start printing error messages in console or in logs. And this example also came from our real experience on the production system, where we saw in the logs similar kind of exception messages, but unfortunately, this exception message didn't contain a stack trace. But we didn't how to find the reason of these exceptions without modifying the code. So we can use Async-profiler again. So besides profiling native functions, it can also intercept or hook Java functions or Java methods, sorry. So now, as an event type, I can put Java method name here, fully qualified name with a class name, null pointer, null pointer exception, and you'll find all places where the constructor of null pointer exception is called. Already drawn. So here it is. These are our null pointer exceptions, and with the full stack trace of the code where it is created. So even if the stack trace is not printed, we can still recover it using Async-profiler. By the way, it's of course possible to profile not only exceptions, but any other Java method, or even all methods in a given class. So it's possible to put a wildcard.
So with the star, whenever we call anything from null point exception, we'll see it on the graph, right?
Yeah.
Cool.
Okay, didn't try it, but let me just do some improvisation. Like let's find all methods from print stream in our applications. Yeah, here are they.
Oh, cool. So they will be on the top, and yeah, yeah, that's really nice feature. Yeah, and probably leads us to another question with this very relates to what we do in Millennium. That's very common pattern where you have a small function which runs very, very fast, and the others at the time basically application just check something. So if we run Async-profiler against it, it will say, okay, yeah, I hit a lot of checks, which application does on a regular basis, but we don't hit, or maybe hit very little that small small function, small operation. How to manage that?
So I'm not sure I quite understood the question. So the question is that how to find the well, application does a lot of things, but we are interested in a particular function. We just want to find to profile only this thing.
Yeah, which runs very, very fast. For example, store 100 micros.
Well, there are two options here. Not perfect though, but still one option is to reduce the profiling interval by the way, and I told that there is an option -I to set the interval. By default, it's 10 milliseconds. So we can reduce it to a smaller value, like say 100 microseconds. Smaller intervals, well, it's probably the smaller intervals can cause a large overhead of the profiler, so I wouldn't recommend to use them in production. But 100 microseconds, in some cases, it's okay. Well, and then after getting the flame graph, we may use include or exclude options to filter only interesting stack traces. Another option is to explicitly turn on profiling at some points and turn off them afterwards, like we did it before with Java API. And there are also options recently added in Async-profiler 2.0 begin and end, which will cause the profiler automatically start and stop when the execution reaches the given native functions. But unfortunately, it's not possible to start profiling Java functions yet, only native functions.
Okay. Okay, got it. Thank you. So begin and just for native only.
Yeah.
So do you think that it's possible to make it possible for Java?
Yeah, I think so. But for Java, as I told before, it's possible to use Java API directly. But of course, if you can afford modifying the source code.
Sure. Yeah, thank you.
Okay, told about that and Java methods as well. So, well, maybe let's wrap up. Well, there are multiple ways to contribute to Async-profiler. So they're probably the easiest one for you, and at the same time, very important for me is to try it, use it, and provide feedback. Write post tweets, write blog posts, like these couple of blog posts that I didn't even have relation to. They just appear describing their experience with Async-profiler. So if you have questions, you want to report bugs or request new features, so there are mainly two ways to do that. Is to, of course, GitHub, go to issues and post your question or feature request. And there is also a dedicated tag on Stack Overflow, which I monitor. So ask a question with this specific tag, I'll definitely see it. Okay, code contributions are also welcome. So mostly I'm always happy with documentation updates, because I'm like probably many developers don't really like to write documentation myself. But if you hit some problem and found how to solve it, there is a good opportunity to help other who may hit the same problem too, and update the documentation. So bug fixes are also welcome. As to features, I put a question mark here because, well, first of all, because if you are working on the big feature in Async-profiler and want to, and then create a pull request to integrate it into main repository, so most likely it won't be immediately accepted. So it's better to start discussion and just open an issue for discussion, and we can come up with a possible solution and a way how to solve this problem. Because what feature is probably good for you is not necessarily aligns well with the idea of well, with architecture of the profiler, or I can probably suggest a better way to deal with it. For example, I had a pull request about porting Async-profiler to PowerPC, and well, even if I accepted this pull request, this could be easily broken because I don't even have PowerPC hardware, can't test it, and so. But at the same time, what I see a good way to handle such situation is that when you commit the things in the shared code that are not related to your particular need, and these changes are perfectly okay, and can create a downstream repository with your own changes, and then if there are supporters for it, we can discuss about integrating it into our main line as well. Well, yeah, thought about that, and once again, thank you very much for your patience for so long time hearing me.